Good evening to all and welcome to week 4 of the problem solving session. So am I audible to everyone?
Yes, ma'am, you are audible.
Okay, thank you. Okay, for the week 4, the topics mainly covered about the stability of linear system and also weakly linear systems. So for linear autonomous system, we know that the system description is given as x dot equals to ax. So how can we what can we tell about the stability of this system? So obviously for linear autonomous system, it is sufficient to tell stability about the solution x equals to 0 because the system has the unique equilibrium at x equals to 0. Okay, so any solution will be stable if this equilibrium solution is stable. Then how can we characterize it? Based on this system matrix A. So that is covered using some theorems that is there in the recorded lecture. So what it says that every solution of this linear autonomous system will be stable if all the eigenvalues of matrix A have negative real part. So if A has all the eigenvalues having negative real part, then we say that system is stable. Sorry. The second part of theorem covers that if A has at least one positive real part eigenvalue. So if there is again any eigenvalue whose real part is positive, if at least there is one such eigenvalue, then the system will be unstable. What if we have imaginary eigenvalues? Sorry. So for system, for matrix, just a second. Okay. Yes. Now for system, for matrices, when we have all eigenvalues, if we have all eigenvalues have real part less than equal to 0 and there are no eigenvalues having real part greater than 0 or positive real part eigenvalues, but there are some eigenvalues which are imaginary, means some eigenvalues if they lie exactly on imaginary axis, means those can be written as lambda j equals to I sigma j, where sigma j is not equal to 0. So we have eigenvalues having real part less than equal to 0, and we have no eigenvalue having positive real part, but we have some eigenvalues which are exactly imaginary, and these eigenvalues have multiplicity of algebraic multiplicity, obviously algebraic multiplicity of kj. Okay, so what it means, so we have an imaginary eigenvalue lambda j, this is having multiplicity of kj, so lambda 1 is having multiplicity of k1, lambda 2 having multiplicity of k2, and these are purely imaginary eigenvalues. Then the solution will be stable if and only if for those imaginary eigenvalues lambda j, the matrix A has kj linearly independent eigenvectors. What it means? It means that those eigenvalues which are purely imaginary should have algebraic multiplicity equal to geometric multiplicity. If we have such scenario, then the solution will be stable. Otherwise, if there is any case where this geometric multiplicity is less than algebraic multiplicity for that repeated eigenvalues which are purely imaginary, then the system will be unstable. Okay, so this was about linear autonomous systems. Sorry. Then we have the notion of asymptotic stability. So what we meant about stability just guarantee about the boundedness of the solution. So if all the solutions, if I start nearby the equilibrium point, if I remain in some epsilon neighborhood, then I call that the solution is stable. But asymptotic stability tells us about the convergence of the solution towards the solution of interest. So it says that so the definition is like this: a solution x equals to phi t of any system, if I'm talking about, is asymptotically stable so first obviously it should be stable, means it should be bounded. If it is stable, and also if every solution given as psi t which starts sufficiently close to the solution phi t, or the equilibrium point, we can say, must approach phi t as t tends to infinity. So suppose if I'm talking about the stability, asymptotic stability of the origin, what does it mean? Suppose x equals to 0, this is my phi t. When will this be asymptotically stable? If every solution which starts sufficiently close. So I'm talking about scalar system here. So if I start sufficiently close, so this is my solution, x equals to phi t, which is the equilibrium point, equals to 0. If I start sufficiently close to it, suppose I start from 2, and my solution phi t will converge to 0, or if I start anywhere which is close to this point. So let's say I start from -4, and my trajectory or my solution will converge to 0 as t goes to infinity. Then we say that the solution is asymptotically stable. So if I draw a trajectory, suppose this is time and this is x of t, and I am interested in the equilibrium x equals to 0, and suppose my trajectory starting from here goes something like this, and then I have another system yt. Here also I am interested about the equilibrium y equals to 0, and this y is having trajectory like this. So which among these, A or B, is stable and which one is asymptotically stable? Whether A is stable or asymptotically stable? As we can see from the graph A, that the solution x, it is starting from some point, okay, it can be value 2 or 3, and it is decaying, but it is not decaying to 0. I'm interested in the equilibrium x equals to 0. It is decaying to some finite value but not 0, okay, and as t goes to infinity, it stays on that value only, okay. So what can we say about this system A? Is it stable or asymptotic stable? Anyone? Since it is not decaying to 0 as
So it is
t,
stable, ma'am. A is stable.
yes, A is stable,
B is asymptotically stable.
yes, and B, since we can see from here that the trajectory y or the solution y is converging to the equilibrium point, which is y equals to 0, so this is asymptotically stable. Okay, now the third part which is covered is stability of the system. Let's generalize it to system x dot equals to fx, where f can be a non-linear function of x. Then how to characterize, then what can we say about the stability of this system? So for linear system, since we have only a single equilibrium point which is 0 and which is unique, we can say the system is stable, because we obviously that means we are talking about stability of the only equilibrium point which is 0. So it is perfect to say that the system is stable or unstable, because we are always talking about that only one particular equilibrium point. But for non-linear system, we cannot just say the system is stable or unstable, because the system can be stable for one region and can be unstable for another region. So that comes from the equilibrium point, because for nonlinear system there could be one or more equilibrium points. So we have to talk about stability related to that equilibrium point, not just the system as a whole. We cannot say that the system is stable or unstable. We have to talk about the equilibrium point is stable or unstable. So for that, then how can we characterize it? So the first thing is we have to calculate its equilibrium points, obviously. Because equilibrium points are those points, if I start at the equilibrium point, I remain at that point, okay, because at that point the dynamics is zero. So if I am starting exactly at the equilibrium point, I will go nowhere. I will stay on that point forever. So that is what equilibrium point means. So we choose equilibrium point to characterize the stability and instability for nonlinear system. And then we linearize that system about the equilibrium points. And after linearizing, we use these notions to tell about the stability of the nonlinear system about that equilibrium point, not on the whole state space but on near about that equilibrium point. So suppose there are three equilibrium points and I linearize the system about that one equilibrium point, then I will talk about stability, asymptotic stability or instability in the neighborhood of that equilibrium point only, not in the whole region. So first I find out the equilibrium points and I linearize it, and then I will say that the system will be asymptotically stable about the equilibrium solution if the linearized system is asymptotically stable. Means if all the eigenvalues have real part less than 0, or we call it stable in the same way. And then I will say the system is unstable if there is at least one eigenvalue whose real part is less than 0. And we cannot comment on the stability or instability if there is at least one eigenvalue whose real part is 0. Okay, so this is how we characterize the stability of system of the form x dot equals to f of x. So if it has all the real parts less than 0, then the system will be asymptotically stable. If it has at least one eigenvalue whose real part is greater than 0, then the system will be unstable. And if any eigenvalue is having real part 0, Means if we have any purely imaginary eigenvalue, or if anyhow real part is 0, then we cannot comment on the stability of such systems. Okay, so this was all about that is discussed in the recorded lectures. So now let's take some questions based on that. Okay. So let's start with a simple question. So consider system which is given as the following differential equation. X1 dot is 2x1 minus x1 x2, and x2 dot is 2x1 square minus x2. Find all the eigenvalues and comment on the stability. Please try it. Okay, what are the equilibrium points for this system? For that we need to equate the dynamics to 0 and solve for x1 and x2. So let's try to find the equilibrium points. We have x1 dot is 2x1, which I can write as 2 minus x2, and then I have x2 dot, which is 2x1 square minus x2. So from equation 1 we have to solve it for x1 dot equals to 0, which gives x1 as 0 and x2 as 2. Now if I put x1 as 0 here, so here also I have to solve for x2 dot equals to 0, which gives us 2x1 square, 2x1 square equals to x2. Okay, since the second dynamics gives us the relation between x1 and x2. So for x1 equals to 0, let's put it here, which gives us x2 equals to 0. And for x2 equals to 2, for x2 equals to 2, x1 will be plus minus 1, x1 will be, it will give us x1 square equals to 1, which is x1 equals to plus minus 1. Okay, so what are the possibilities of all the equilibrium points? So first equilibrium point, if x1 is 0, that will make the first dynamic 0, that will make the second dynamic 0 only when x2 is 0. So the first equilibrium point is x1 0, x2 0. What about the second one? So there is only one possibility with x1 equals to 0. Then we have x2 equals to 2. So for x2 equals to 2, we got the solution as x1 equals to 1 or minus 1. So you can check by putting x2 equals to 2 and x1 equals to 1, that will give both x1 dot and x2 dot as 0. So our another equilibrium point is 1 comma 2, and third will be minus 1 comma 2. Is it okay?
Yes, ma'am.
Now then we have to comment on the stability. So since this system is nonlinear system, we cannot comment on the stability of the system, but we have to check stability about the solution, and the solutions are these three equilibrium points. Okay. Now what can we say stability of the system about the first equilibrium point? So the step is we have to linearize the system about this equilibrium point. What is the step of linearization? How can we linearize it? Let's write the system. So our system of interest is 2x1 okay, we have to linearize about e1, which is 0 comma 0. Now in order to linearize it, we have to find its Jacobian, and Jacobian is nothing but del f upon del x, we all know. So this is my f1, this is my f2. Okay, so the Jacobian, since it is a second order system, the Jacobian will be 2 cross 2, which is del f1 upon del x1, del f1 upon del x2, and del f2 upon del x1, and del f2 upon del x2. So this will be my Jacobian, and I have to evaluate it at 0 0. This will be the linearized system, linearized dynamics at this equilibrium point. Okay, what will be del f1 upon del x1? Partial derivative of x1 with f1 with respect to x1. What it will give us? 2 minus x2. What about the second element, del f1 upon del x2? It is minus x1. The third element, with respect to x1 it is 4x1, and with respect to x2 it is minus 1. What will be its value at 0 comma 0? So we have to put x1 as 0 and x2 as 0. So it is 2, 0, 0 and minus 1. Okay. Means nearby, in close neighborhood of 0 comma 0, the system follows this dynamics. Okay, this is what it means. And now what can we say about the stability at this equilibrium point? What are the eigenvalues of this matrix? What are the eigenvalues of this matrix? it's a diagonal matrix, so it will be nothing but
2 comma minus 1.
yes. So lambda 1 is 2 and lambda 2 is minus 1. Now what can we interpret from here? We have one eigenvalue having positive real part 2, right? So we have found one eigenvalue which is positive. So we can conclude that the system is unstable about the origin. Now similarly we have to evaluate for the second eigenvalue, which is 1 comma 2. Now since we have already determined our Jacobian, we have to just evaluate it that at that point. We have to evaluate it at 1 comma 2. That will give us 0, minus 1, 4 and minus 1. Now what are the eigenvalues for this matrix? You can use MATLAB to find the eigenvalues. So if you check, the eigenvalues will be so lambda will be minus half plus minus j root 15 by 2. Then what can we say about this system? Stability about this equilibrium point? Since
So real.
the eigenvalues have negative real part, we can say that the system is stable or asymptotically stable. Now similarly, uh, tell me about the third one, which was minus 1 comma 2. So evaluating the Jacobian at this point will give us 2 minus 2 will be 0, this will be 1, minus 4 and minus 1. This will be our Jacobian at minus 1 comma 2, and this will give us the same eigenvalue. So lambda will be same, it will be minus half plus minus j root 15 by 2. For this case also we have negative real part, so the system is stable. Okay, so what does it mean? It means that we have a system of two variables x1 and x2. If I start nearby the origin, I will not remain nearby, I will go unbounded. That's what we got, because at origin we have one eigenvalue as positive, means I am not going to stay bounded. Now for the second one we have if I start nearby this 1 comma 2 coordinate, so if I start such that my x1 is close to 1 and x2 is close to 2, then I will converge to I will remain stable and I will converge to this 1 comma 2. Now similarly for minus 1 comma 2, if I start nearby it, I will converge to this equilibrium point minus 1 comma 2. So this is how can we characterize the stability of nonlinear system. Let's take another question. Okay. Again we have system x1 dot as x2, x2 dot is minus x1 plus x2, and 1 minus 3 x1 square minus 2 x2 square. Find again the equilibrium points and comment on stability. Okay, what are the equilibrium points for this system? So equating first dynamics equals to 0 will give us only one solution, which is x2 equals to 0. Okay, and the second dynamics, which is minus x1, if I evaluate this to 0, now since x2 should be 0 for the first dynamics to be 0, so let's put x2 equals to 0, and that will give us minus x1. This, since this term is 0, all this term will vanish, so it is x1 equals to 0. So the only solution or the only equilibrium point that we get is 0 comma 0. There is no any other possible equilibrium points for this system, and so we have to check the stability about this equilibrium point. So again we will find the Jacobian. This is f1, this is f2. So derivative of f1 with respect to x1 is 0, with respect to x2 it is 1. For f2, its derivative with respect to x1 will be minus 1, and this term will be 0, and this will be minus 6 x1 x2 and nothing else. And the last part will give us with respect to x2 it will be 1 minus 3 x1 square and minus, it will be 3, so 6 x2 square. So this will be the Jacobian, and we have to evaluate it at 0 comma 0. That will give us 0, 1, minus 1 and 1. This will be my Jacobian at 0 comma 0. Now what are its eigenvalues? Let's try to find the eigenvalues. Minus lambda. So it is lambda square minus lambda plus 1. So lambda will be so it is half plus minus root 3 by 2 or j by 2. So the eigenvalues having real part of lambda is greater than 0. So what can we conclude? Whether the system is stable or unstable?
Unstable.
Unstable. All right. Moving on to next question. Yes. Okay, this is related to some previous topic, but just as a brush up, let's take that question. Okay, so we have system of the form x dot equals to f of x, where this fx, which is a nonlinear function, it is given as minus x1 plus x1 x2, x2 minus x1 x2. Okay, and we are interested in the region D, which is given as x belongs to real number, obviously in the two-dimensional Euclidean space, and I am in the rectangle where x1 is less than equal to a1 and x2 is less than equal to a2. You have to calculate the Lipschitz constant of fx. What will be the Lipschitz constant of the function fx, which is a vector minus x1 plus x1 x2, x2 minus x1 x2. Now since we can see that my fx is continuous as well as differentiable because there is no any such term, So since the system is continuous as well as differentiable, the Lipschitz constant can be calculated using the norm of the partial derivative. Okay, so how can we calculate the norm of a partial derivative? So the partial derivative of a function f is nothing but the Jacobian. So for that we need to calculate the Jacobian of this f. So what will be the Jacobian? We have f1 as the first element minus x1 plus x1 x2, and f2 is x2 minus x1 x2. Now we have to calculate, let's del f by del x, the Jacobian. That will be given as the norm of the Jacobian, or here we call it the partial derivative, is nothing but the Lipschitz constant. Okay, let's calculate its Jacobian. So evaluating for f del f1, what will be del f1 upon del x1? It is minus 1 plus x2. Now what will be the second element? Del f1 upon del x2, it is x1. What is del f2 upon del x1? Partial derivative of f2 with respect to x1, it will be minus x2. And similarly del f2 upon del x2 will be nothing but 1 minus x1. Okay, so this is my Jacobian. Okay, now how can we find out the norm for this matrix? Okay, so since all the norms are equivalent, we can, the infinity norm of this partial derivative means we have to calculate the norm of this matrix. So we can calculate any norm. So let's uh, take the induced matrix norm, because we have to take the norm of this matrix, and the infinity norm. So let's call this matrix as A. This is nothing but, how can we calculate? We have to take the absolute value of the elements of rows, of each rows, and take its maximum. So it is nothing but maximum of minus 1 plus x2 absolute value plus x1 absolute value, and the second row is minus x2 minus x1. So row wise we have taken absolute and taken the sum, and then for each row we have to take the maximum of them. That will give us the infinity induced matrix norm. Now since we are interested in the rectangle, so what will be the maximum we can have? So the x2 minus 1 can have a maximum of 1 plus a2, and x1 can have a maximum of a1. Similarly, this can have a maximum of a2 1 plus a1. So the maximum is nothing but 1 plus a1 plus a2, because both are same. Okay, so what is the uh, Lipschitz constant for this function f? It is nothing but 1 plus a1 plus a2. Okay, this is how you can calculate the Lipschitz constant if required for a nonlinear system, if given that the function f is continuous, and you can calculate that for any bounded region. So for that you need to calculate the Jacobian in order to calculate the induced matrix norm. So that was one use of Jacobian. So that question covers how we can calculate Lipschitz constant. Okay. Consider this system. X1 dot is minus x1 plus ax2 minus bx1 x2 plus x2 square, and x2 dot is given as minus a plus b x1 plus b x1 square minus x1 x2. Find again the equilibrium points and comment on stability. For a greater than 0 and b not equal to 0. Okay, so this is the system, and so such systems you can think of it like you have a system and you have some parameters which are not accurately known. Okay, so in electrical system many a times we need to design a circuit, and for the fixed topology we sometimes know the differential equation, but we cannot decide on the values of resistor, capacitor or inductor or some elements we need to uh, determine. So for that you can do the stability analysis first by writing down the differential equation and then calculating its finding out its equilibrium point, and then checking on what range of those parameters. So suppose these a and b denotes the values of capacitor and resistor, you can basically check at what range of a and b will give you a stable system or unstable system. So these are the practice for those type of scenarios. Okay, what are the equilibrium points for this system? How many equilibrium points is coming out for the system? Okay, let's calculate it. Anyone calculate it? Okay, let's try to solve this. So we have the dynamical equation as minus b x1 x2 plus x2 square, and x2 dot is minus a plus b x1 plus b x1 square minus x1 x2. Now obviously we have to solve it for x1 dot 0 and x2 dot is 0 in order to find out the equilibrium points. Okay, equating this to 0, what we will get? Or equating this to 0, we can take x1 as common, because x1 we have in both these three terms, so it will be x1 of minus x2 and plus b x1 minus a plus b. This equals to 0 means, sorry, this will be x2. Okay, this equals to 0 means x1 equals to 0 is the obvious solution. Or another solution will be this part as 0. Equating this part to 0 will give us x2 equals to b x1 minus a plus b. Okay, so second dynamics equating 0 gives us these two solutions. Now let's put x1 equals to 0 here and see what solution we will have. So x1 equals to 0 means we have a x2 plus x2 square as 0. That means x2 plus a equals to 0. So this will give us x2 as 0 and x2 as minus a. Alright. So first equilibrium point will be, for x1 equals to 0 we have x2 as 0, and second we have, for x1 equals to 0 we have another solution, x2 equals to minus a. Now we can have another equilibrium point because we have this solution also, x2 equals to b x1 minus a plus b. What you will get if you put this x2 over here? Let's try to solve it. We have x2 is b x1 minus a plus b, and for x1 dot equals to 0 we have minus x1 plus a x2 minus b x1 x2 plus x2 square. Now if I put x2 as this over here, it will be minus x1 plus a b x1 minus a plus b minus b x1. So it involves some calculation, and again we have b x1 minus a plus b. Okay, think I have done some mistake in calculation. This minus x1 plus. Yeah, this square. Okay. Okay, so when you solve it for equal to 0, what you will get, x1 equals to ba plus b divided by 1 plus b square. Okay, now when you put value of x1 over here, that will give you x2 as minus a plus b divided by 1 plus b square. Okay, so you can calculate and check. So in summary, you will have three equilibrium points. So first one is this, second one is this, and the third one is this equilibrium point. And then you can find out the Jacobian and then comment on the stability of each of these equilibrium points. Okay, so let me write all the equilibrium points. So the first is 0, second is 0 comma minus a, and the third is ba plus b divided by 1 plus b square and minus a plus b. Okay, let's check on this trivial equilibrium point 0 0. Okay, because the rest of the others will involve some calculation. Okay, this f1 for this question is, it is here. Let me write it here. It is minus x1 plus a x2 minus b x1 x2 plus x2 square, and f2 is minus a plus b x1 plus b x1 square minus x1 x2. Find out the Jacobian for this function. Find out this matrix. What will be the Jacobian for this one? Please calculate. Okay, what is it? The first element will be, what will be the first element of Jacobian?
-1
Minus 1
minus bx2
minus bx2. That's all. The second element, so it will be
a minus bx1.
minus,
Sorry,
yes, we have another element also. It is minus bx1 and then 2x2.
x2.
Third one will be minus a plus b and plus 2b x1 minus x2, and the last will be minus x1. Okay, now we have to evaluate it at 0 0.
Ma'am, the position 2 comma 1, please verify again. In Jacobian.
This position,
Yes, ma'am.
so we have to take del f2. We have to find out the partial derivative of f2 with respect to x1, means we have to find its derivative, partial derivative with respect to x1. So this will give us the partial derivative of first term with respect to x1 is just the constant term, which is minus a plus b. Okay, second term, it will
Yes, ma'am.
be,
Fine. Yes, ma'am. Fine. I got.
yeah, okay. So at 0 comma 0 it will be minus 1 a minus a plus b and then 0. Okay, now what can you say about the stability, considering that a is positive and b is not equal to 0? So these constraints you often have in electrical circuits, where suppose a is the value of resistor and b is a value of capacitor. So obviously the parameter should be positive and you have to include a capacitor in your system, so this should not equal to 0. So in practical scenarios you can think of it like this. What are its eigenvalues? Obviously it will come in terms of a and b. What are they? So if you solve for the eigenvalues that you will get will be minus 1 plus minus under root of 1 minus 4a a plus b divided by 2. Now what can you say about this eigenvalue? So if a is positive and b is not equal to 0, if a is greater than 0 and b is not equal to 0, that means this under root term can be positive or can be negative also, and that depends on the value of a. Okay, so for different regions of a you can actually evaluate how this eigenvalue will be. Now suppose this a uh, is greater than, let's say, 1 and b is also greater than 1, then this term 4a into a plus b will always be greater than 1. That means the under root term will be negative, and hence we have imaginary eigenvalues with real part negative. Okay, if you choose a greater than 1 and b greater than 1, then your eigenvalues will be imaginary with real part negative. So that means the system is going to be stable about the origin, about the equilibrium point 0 comma 0. So any question?
No, ma'am.
Okay. consider a system. So basically, okay, so let's call it, which is given as y double dot plus ky. Y is a variable, k is a constant, c is also a constant, plus sine y equal to 0. Okay, convert this into state space form. And find out the equilibrium points. So we have a second order system whose differential equation is y double dot, means double derivative of y with respect to time, plus k into y where k is a constant, plus c into y dot, c is also a constant, plus sine of y equals to 0. So first convert it into a state space form and find out the eigenvalues. Or state space, yeah, we can say it as a state space, or you can say convert it into first order equations. So in order to convert it into first order equations, since it's a second order equation, we need to fix two variables. So let's call those two variables as y1 and y2. What variable we can take y1? We can take y1 as y, and y2 we can take as y dot. Okay. After fixing the variables, we have to now calculate y1 dot and y2 dot, and this will give us the first order representation of our system, y double dot plus ky plus cy dot plus sine y. So what will be y1 dot? So y1 dot is nothing but y dot. Okay, y1 dot is nothing but y dot, and y dot is nothing but y2. So that means y1 dot is y2. Now similarly, what is the y2 dot? Y2 dot you can take from here. Y2 dot is double derivative of y. Okay, and what is double derivative of y? You can find from the system equation. It is minus ky minus cy dot minus sine of y. Okay, now since we have to write everything in terms of y1 and y2, that means, so instead of y we can write y1 from here. So y is nothing but y1, y dot is nothing but y2, and similarly y is nothing but y1. So what is the dynamical equation for y2? Y2 dot is minus k y1 minus c y2 minus sine y1. Okay, let's write it neatly. So we have y1 dot as y2 and y2 dot is minus k y1 minus c y2 minus sine y1. Now can you find out its equilibrium points? What are the equilibrium points for this system? Anyone? Okay, equating the first dynamics as 0 will give us y2 equals to 0. Okay, this is the only condition to make y1 dot as 0. Now since y2 is 0, for y2 dot equals to 0, we have minus k y1 and y2 is 0 from first equation, so it is 0 sine y1 equals to 0. Okay, and this will be 0 only when we have the only possibility that we have for this equation to be 0 is
y1 equals to 0.
y1 equals to 0. So for this system we have the unique equilibrium which is 0 comma 0. Now can you quickly tell me about the stability of this system about the origin, because 0 0 is the equilibrium point. What is del f by del y? This is f1 and this is f2. So del f1 by del y1 is 0, del f1 by del y2 is 1. Similarly, del f1 by del y1 is minus k and minus cos y1, and similarly del f2 by del x2 del y2 is minus c, and evaluating it at 0 0 will be 0 1 minus k minus 1, cos 0 is 1, and then minus c. So this is our Jacobian. Now you can calculate its eigenvalue. So for eigenvalue we have minus lambda 1 minus k and minus c minus lambda. For determinant equating to 0 will give us minus c minus lambda and plus k plus 1 equal to 0. So it is lambda square plus c lambda plus k plus 1. Now obviously you can look from here that the nature of eigenvalue depend on the value of c and k. So for any system you can find out c and k to have a stable system or to have an unstable system, because lambda will be minus c plus minus under root c square minus 4k plus 1 by 2. So you can select c and k to make the system stable or unstable. Now suppose C is positive. Now we can leave that part. Anyways, similar to this question, find out all the equilibrium points of x1 dot is x2 cos x1 and x2 dot is sine x1. Find the equilibrium points. Okay, equating first dynamics as 0 means x2 cos x1 is 0. So this is possible when x2 is 0 or when x1
This one
is
is 0.
no.
Sorry. No. Cos 0 is 1.
What should be x1?
2n plus 1 pi by 2.
Yes, the odd multiple of pi by 2. So it is 2n plus 1 pi by 2. Okay, all the odd multiples of pi by 2 will make cos x1 0. So first equation gives us these values. Now what about the second one? Equating x2 dot at 0 gives us sine x1 as 0, and sine x1 will be 0 only when x1 is
n pi.
n pi. Okay, so what are the values for which we have equilibrium points? What are the equilibrium points for this system? Obviously odd multiples, both positive and negative multiples of pi will make sine 0. What are the equilibrium points? So these are the values of x1 and x2 for which x1 dot is 0 or x2 dot is 0. On what values of x1 and x2 both x1 dot and x2 dot is 0? Because we are interested in the equilibrium points, means simultaneously x1 dot and x2 dot both should be 0. What are those points? Okay, let's see. The first dynamics will be 0 when x2 is 0 or when x1 is odd multiple of pi by 2. So if we take x2 as 0, okay, then x1 should be plus minus n pi. So the equilibrium point, one equilibrium point should be plus minus n pi comma 0, this set. This is actually not a point but a set of equilibrium points, right? Because n goes from 1 to any number, any natural number, 1 to infinity. So this gives us all the sets of equilibrium points, not only a single equilibrium point. Is there any another possibility? Now to make x1 dot is 0, cos x1 can also be 0. That means we can have odd multiples of pi by 2. But at odd multiples of pi by 2, sign will not be 0. That means x2 dot will not be 0. Okay, so the only possibility for both these dynamics to be simultaneously 0 is x2 0 and x1 to be plus minus n pi. Okay, so this is the only set of equilibrium points for this problem. Okay, we are only discussing about the equilibrium points up to of system up to second order. Now let's increase the order to 3. Suppose we have system. Obviously, as you go on, it becomes really difficult to calculate the Jacobian and analyzing the system as the size increases. Okay, so we have a simple third order system. So for this one, find all the equilibrium points and then comment on stability. So this will be the last question for today's session. Obviously there could be complex problems, but uh, the concepts will remain the same. If you are firm with the concept, then you can solve any complex problems. So to find equilibrium point, we have to simultaneously solve for all these three derivatives to be 0. Okay, so simplifying this one is, okay, so this first derivative will be 0 for x1 0. Another possibility is that x1 square equals to 2. That will also make x1 dot as 0. So x1 square equals to 2 means x1 can be 2 and minus 2. So for these values of x1, x1 dot will be 0. Now let's solve for this. x2 dot will be 0 when x1 square equals to x2. Alright, we will check on this. And x3 dot, this will be 0 only when x3 equals to 0. Okay, so to find the equilibrium point, x3 should be 0 because only when we have x3 dot is as 0. Okay,
Ma'am, this x1 is 0 comma plus minus root 2, I think.
oh yes, sorry, correct, thank you. It is plus minus root 2. All right, then so x3 we don't have to worry much because x3 should be 0 for x3 dot to be 0. Now we have to select values for x1 and x2. So first let's start with x1 equals to 0. At x1 equals to 0, x2 will be 0 only. So the first set that we have is 0, 0 and 0 because x1 0 makes x2 0 and x3 should be 0. So at this point this x1 dot, x2 dot and x3 dot all are 0. What about the second one? For the second one we have to pick another value of x1, that is root 2. So let's pick x1 as root 2. If x1 is root 2, what will be x2? x2 will be 2 and x3 is 0. Now let's pick another value of x1 which is minus root 2. At minus root 2, x2 should be 2 only and x3 is 0. So these are all the equilibrium points for this third order system. Is there any other possibilities?
No, ma'am.
No. So these are the three equilibrium points for this system. And similarly for this case also you can check on the stability at each of these equilibrium points. So just as a practice, let's check the stability of about the solution at 0 0 0 means at the equilibrium point 0 0 0. Let's check the stability of the system. So what will be the size of Jacobian for this problem?
3 by 3.
3 by 3. So it will be del f1 del x1 del f1 del x2 del f1 del x3. Similarly for second second row we have del x2 and del f2 upon del x3, and similarly for the third row we have derivative with respect to x1, with respect to x2 and finally with respect to x3, and this we have to calculate about 0 comma 0 comma 0. If we do so, what will be the first element? It will be minus 2 plus 3x1 square. What will be the second element? It is 0, and third element will also be 0 because there is no x2 and x3 in f1. What about the second row? We have to focus on this. So it is 2x1. Derivative with respect to x2 is minus 1, and there is no term of x3, so it is 0. Now for the third row, let's focus here. So there is no term of x1 and x2, so this is 0 and this is 0. The third element is minus 1. Now at 0 0 0 this goes to 0, so we will left with minus 2 only. It is minus 2, and this also goes to 0 at 0, so it is 0. Now what are the eigenvalues?
Minus 2,
Minus
minus
2,
1.
minus 1, minus 1.
Yes, minus 2, minus 1 and minus 1. So all the eigenvalues have negative real part. So this is is it stable or unstable?
Real part is negative, that means it should be stable.
Yes, it is stable. All the eigenvalues have negative real part, so it is a stable system. Stable about the equilibrium point 0 0 0. Okay, not on the whole region, but only about in the neighborhood of this equilibrium point. Similarly, you can check for all other equilibrium points also. So this covers the topics of week 4, and I think in the next week it will be about how to draw the phase portrait. So let's meet in the next week if you
Ma'am,
have
I
any
have a
doubts.
ma'am. Excuse me, ma'am. I have
Yes.
a doubt in assignment question number 7. How to solve this, ma'am? Can you give a hint?
What is that?
Consider a system of differential equation x
Mm-hmm.
dot is equals to a matrix 3 cross 3 matrix 3
Mm-hmm.
4 in a I'm telling in a row 3 4 minus 2 2 1 minus 4 1 2 0 into x plus 1. It is a column vector, ma'am. 1
Okay.
minus t and sine t. Then solution of this problem is stable, unstable, and asymptotically.
Okay. Okay, so basically it is a non homogeneous system, and it is covered in the lecture that for non homogeneous system you have to consider the stability with respect to x. If your system is x dot equals to ax plus some function, right? It is of that form. So it is basically a non homogeneous system, and it is covered in the recorded lecture that if G is of some form, and I think in that question it satisfies that form, then the solution stability of the solution will be considered with respect to the stability of the system x dot equals to ax. So whatever the solution, whatever your interpretation is for the linear system, that will be same for your non-autonomous system.
Okay, ma'am. If I will calculate the eigenvalues, then I can
Of
find
a,
these steps.
yes,
Okay,
then you
okay.
can interpret for that also.
Okay, thank you, ma'am.
Okay. Okay, let's meet next week for some more problems. Thank you for joining today's session.
Thank you, ma'am. Thank you.